Here we have our second lecture for Chapter 3, where we'll learn about percentiles and the 50-34-14 rule, also known as the normal approximation rule. So you'll recognize this from our last lecture. This is a picture of the normal distribution with the z-scores written in on the bottom, and you'll recall that the mean is 0 and the standard deviation is 1, and that's what's indicated beneath all of these gray lines. Well, there are some characteristics of this distribution that will help us with our subsequent questions that may arise. So first of all, we know that in this distribution, half of the scores lie above the mean, 50%, and half of the scores lie below the mean. So if someone has a z-score of 0, we know that their score is higher than half of the other participants, and we know that her score is lower than 50% or half of the participants. So that's pretty straightforward. So the next rule, approximately 34% of scores lie between 0 and 1 standard deviation above the mean, and 34% lie between 0 and 1 standard deviation below the mean. We know that approximately 14% of scores lie between 1 standard deviation and 2 standard deviations above the mean, and approximately 14% lie between -1 and -2 standard deviations. And finally, we know that approximately 2% of the values are going to lie in the upper tail of the distribution, and about 2% are going to lie in the lower tail of the distribution. So now that we know these basic rules, we can solve some problems. And there is that last bullet point. So now let's give ourselves a person. Let's give ourselves someone who has a z-score equal to 1. So here's our person, z1 equals 1. Here is this person's score. And so if we wanted to know how many people or what proportion of people did she surpass in terms of her score, we can simply count up the proportions that are below her. So we would have to count up the proportion of the values that are in this cell, in this region of the distribution. And we know that that's 34%. I'm going to see if I can get a fatter tip on my marker here. And no, I don't think I can. That's okay. So we know that about 1/3 of the scores are going to be right here. So here's our marker score in green. So let's go ahead and write our 34% to correspond to this area. We know that we have to get all of the scores in this one because it is lower than her score. And that's another 34%. Whoops. 34%. We know that we have to get the proportions that are in this section. And we can see that that is 14%. And we have to get the scores or the estimated proportions that are in this little tail. which is approximately 2%. And so if we add all of these together, 34 plus 34 plus 14 plus 2, 68, 78, 82 plus 2 is 84%. So if our person, let's call her Abigail, had a z-score equal to 1, we can say that she had a score that was higher than 84% of the other individuals. We could also say that her score was in the 84th percentile. And we'll define percentile on the next slide. You could also count up the scores that are higher than her score. And if you added these scores up in this region, 14% plus 2%, you would see that that equals 16%, and you could say that 16% of individuals had scores higher than her score. This is called the 50-34-14 rule, or the normal approximation rule, and we'll be working with this in our class today. So here is the content that we just talked about, written up in a little bit different way. And let's go ahead and add the 2% to the tail down here, approximately 2%, and 2% here, and that accounts for all of these going off into infinity. So, what is a percentile? It's the percent of values below a given score in a normal distribution. So let's give another example here. We would just sum the percentages lower than the z-score to find the percentile. So we just did this with an example of 1, but we'll look at it now a little bit neater in case it wasn't clear. Carla's z-score was 1 for her math test. Her score was higher than what percent of people who took the test? So if we plot Carla's score of 1, you can see it right here. And so in order to know how she did, we have to add up all of the scores in this yellowish region. And we discover, as we showed before, that the 34% plus the 34% plus the 14 plus the 2 equals 84%. And that means that she is in the 84th percentile. You'll see this word percentile used when you get, say, your child's test scores back, and they will show up as, they'll tell you how your child did or ranked, or what proportion of other children their score surpassed, and that's what that 84th percentile means. It doesn't mean they got 84% of the items correct. It means that their score falls above 84% of the other individuals. So far we have calculated these by adding together all of these lower values. We could also shortcut it by just taking this 50% to start with, right? Because we know we're getting all the scores lower, so we could take the 50%. Now we've accounted for all of this region, and we could add the 34%, accounting for this region. We get, again, 84%. Another way that we could do it, you may have noticed that all of these add up to 100%. So another way we could do it is to just take these two little sections on this side of the distribution, the 14 plus 2, and subtract it from 100. So another way to do it would be 100% minus 14 plus 2, which also equals 84%. So there are a number of ways that you can work with this kind of situation. So once again, the percentile is just the percent of scores below yours in a normal distribution. And if this is you, and we have all of these individuals, these 20 individuals, then you are scored higher than 80% of individuals, so you are in the 80th percentile. So we can look at the distribution we were working with in our last lecture and take it a step farther. Let's imagine that Janae had a raw score of 40, and you can see it marked here. So what is her z-score and what is her percentile? Well, we can follow along and see that her z-score is 1. It's right aligned with a 40. And to figure out the percentile, we add up what's in these regions, and we can see the 14% and the 2% from the tail, so we know she's in the 16th percentile. In other words, she scored higher than 16% of the other individuals. Here are a few more that we could solve. Carlos had a raw score of 70. And let's see if we can get that to show up. There we go. So Carlos had this raw score of 70. Here's the 70, and here is Carlos marked. And what percentile is he in? Well, we have to add up all the scores lower than his score. And that's a lot of adding. We'd have to add 34 plus 34 plus 14 plus 14 plus 2. An easier way to do it might be just to take the 100% and subtract the 2%, and we could, if we did that, we discover that of course his z-score is 2 and his raw score is 100% minus 2%, or 98%, and that means that Carlos, with his z-score of 2, is in the 98th percentile. And we did that by just subtracting out this little proportion of individuals who outscored him. If Carl had a raw score of 50, you can see that first here's his raw score, here's his z-score of 0, and you can see just by using this upper 50% indicator that his score is higher than 50% of individuals, placing him in the 50th percentile. And finally, Sarando had a raw score of 65, which is somewhat in the middle here, as you know. Here's the 65, meaning a z-score of 1.5, and that's a little tougher to figure out. So as we have done before, we'll use another tool to figure out those percentiles that are a little bit less obvious. This one's less obvious because it doesn't fall right on the line. We can see that this is where the line will be, but this section is clearly smaller than this section, and so we have to do some work to figure out exactly what the percentile is. So let's continue on. And in your book, this is how you'll see your textbook authors doing this. They'll be using some tables that are in the back of the book that necessitate that you look up the z-score, and then you calculate the difference from the mean to z and the percent and tail, and it's just big tables that you look up. And in the old days, that is how these things were done. You might look up a z-score, for example, of 1.46, and you know where that would fall. A z-score of 1.46 would be 1.5 standard deviations above the mean. And so the percent from the mean to z would be 42.79%. And we know that there's also 50% below the mean, and so we know that this would be in the 92.79 percentile by adding these together. Or we could subtract the 7.21 from 100%. But the good news is you don't have to do that because we don't live in that time anymore. So what I'll show you in a separate video is how to use this indicator. This is a tool that we'll be using for this whole chapter and a little bit beyond. I can't show it to you within this slideshow, but we're going to click on it and you'll watch the follow-up lecture after this to see how to use this calculator. And it'll be an easier way for us to determine what proportion of scores would fall in the tail of a distribution. So in summary, we know that in a normal Z distribution, we know the approximate proportions of scores that fall between the standard deviation lines, and that's that 50%, 34%, 14%, 2%. We can use these approximations to estimate percentiles by summing up the percent of scores above and below a given Z-score. And for scores that don't land right on the standard deviation lines, we can use an online applet to determine the exact percentile for any given Z-score. And that will be the topic of the next lecture.